it's not bad like the day we lost. Anyway, I will begin with a word of prayer. For the first time, anyway, dear Lord Jesus, thank you for this opportunity we have just to meet together and study your creation. Help us to understand abstract algebra better together today. Amen. All right, my apologies if there's overlap. My memory is not very good on what I actually said last time. But yeah, I mean, just to recap problem 61, basically if you can show that the product of two is normal, given normality of both of them, then you can easily like bootstrap your way to 3 or do induction is what the argument says here basically. So I show it for 2 carefully, and then that allows me to prove it for 3 or for n. I think I went through that a little bit more carefully in the last video, so I'll let you look at that in the last help session. Problem 62 here is, yeah, this is a nice little problem. This one's abelian, but you know, if you put a C in the spot where that 0 is, you get a non-abelian group of order 27.
Which 0?
What's that?
Which 0?
Oh, yeah, which 0? Fair question. Let me get my laser. Where is my laser? What have you done with my... Oh, okay. That one. Make that a C, and that'll give you a Heisenberg group. One of the many Heisenberg groups. Anyway, yeah, so you can multiply it out and show it's closed, right? And, well, actually, I mean, this just shows it's abelian. Doesn't show it's closed, I suppose, but actually kind of shows closure in the middle here, doesn't it? Because I multiplied 2 of them, and I got another one of the same thing, so this shows that it's closed under multiplication, right? And although I guess to show it's a group, I should probably still find it's a inverse and such, but I don't think that was the question. The question was just to, it was to show it was an abelian group. And maybe my solution's not unique, it's not complete here, is it? I've showed it's abelian, but I haven't shown it's a group yet. I've showed it has order 9, yeah. And yeah, I think I'm missing a little bit of detail here because I really should show that. I guess there's different ways you could go here. On the one hand, I have not shown that H is a group. On the other hand, I've shown that there's a mapping. If I completed the proof that this really is a bijection and that it preserves the operation on Z3, then that would inadvertently prove that H is a group, because then H would be the inverse image of this group and therefore a group. Well, but then I need I don't know, it's a little dicey. I should just prove H is a group. Otherwise, I might be kind of being circular in my reasoning. So what's missing? I just need to show it's definitely a subgroup of GL3 Z3, right? So all I got to show is it's closed under multiplication and it has the identity, and closed under inverses, I suppose. So what's the inverse of 1AB 0 1 0 0 0 1? It's just what? It's 1 2A 2B 0 1 0 0 0 1. Because when I multiply AB times 2A 2B, I would get 3A 3B, which would be 0 0. And that would translate back to the identity in the multiplicative setting. So, but anyway, admittedly, there's work left to do there. Sorry, my solutions. I would have to take points off my test. I was apparently hurrying too much here. I was so pleased with my proving of the abelianness that I forgot that I do need to show it's a group. So,
because A and B can both be 0.
yeah.
So you kind of inherently get identity.
I don't think closure, inverses, or identity is hard to show, but they should be shown to show it's a group. I could change the wording ever so slightly. Suppose this is a group, show it's abelian, then my solution would have been legit, and this would be fine. Anyway, here's 2 subgroups of order 3. If you've got 2 subgroups of order 3, it's not Z9, right? Because if by the fundamental theorem of cyclic groups, if it's a cyclic group of order 9, it just has 1 subgroup of order 3, just 1. This has 2. At least, I mean, it has more actually, I think, but it's at least got those 2. What's the other subgroup it has of order 3?
There's a 2 minus 1s.
The two ones on the top row? Yeah, yeah. Yep. It's like in the Klein 4 group, you can either generate a subgroup of order 2 by 1, 0, 0, 1, or 1, 1. There's these 3 subgroups of order 2 in Z2 cross Z2. And that's what they look like in this notation. So, yeah. Is one way you could think about it. Here, number 63, we have determined the number of elements of order 15 and the number of cyclic subgroups of order 15 in this. The key concept here, of course, is the least common multiple of the orders is the order of the tuple, like that, right? The pair. And in context, A is from Z30, B is from Z20, so the order of A must divide 30. The order of B must divide 20. You know, so that's pretty limiting. So to get 15 for the order, I either can put 15 here and a 1 and a 5 here. I can't choose 3 here because that doesn't divide 20, so it's not allowed. For 1, there's 1 choice. For 5, there's 4 choices. For 15, or group elements of order 15, you got 8 choices. So that gives us 8 times 5, 40 choices from that case. And otherwise, you've got the order of A is 3, the order of B is 5. In order to get least common multiple of 15, there's 2 of these choices, there's 4 of those choices. That gives you 8. Altogether, 48 choices, 48 elements of order 15 in the group we're looking at. What was it, Z20 cross Z30? And consequently, well, there's that one answer. How many subgroups? 48 elements of order 15. Subgroups of order 15, each one of them has 8 generators. So I have to divide this by 8 to get 6 subgroups of order 15. So,
Question?
sure.
I was just saying, reminds me of a question that we didn't passed on.
Oh, yeah?
I think we had a question on that.
I would say the capstone problem is more like this. But yes, I will. So here I'm supposed to show that there exist 2 abelian groups of order 108 that have exactly 13 subgroups of order 3. Okay. And I may have butchered the wording here. It may have been to show that there are, I mean, you could probably say it, I don't know, this is a nice way. I wonder if it's true if we make the stronger wording. There are, up to isomorphism, there are only 2 distinct isomorphic, 2 up to isomorphism distinct possibilities of abelian groups of order 108 that have exactly 13 subgroups of order 3.
Yeah, it's just to show that there are 2 abelian.
It's a nicer, it's a friendly wording, yes. It has not required us to show that these are the only 2.
Yeah,
Friendly's good.
Yeah. Well, friendly is the difference between a 4-minute test question and a 14-minute test question, right? So 108 is 4 times 27, which is otherwise known as 4 times 3 cubed. And then we use the fundamental theorem of finite abelian groups, which basically says the 4 can either, that 4 gives you either a Z4 or Z4, or it gives you a Z2 cross Z2, right? And this can either be a Z27, or this produces a Z3 cross Z9, or this in the order produces a Z3, Z3, Z3. These are your 3 choices from the 3 cubed. Those are the only abelian groups of order 27 up to isomorphism that we got. What's that?
where you did Z3 cross Z9 twice instead of Z4.
Oh man, yeah, I wanted Z3 cross Z3. Dang it. Okay, I'll stop. Did it matter?
I mean, you can't figure out just on the pound, right?
Did I undo? I wonder if I undid that error in my future thinking, though. All right, so what am I doing? I'm looking for, what was it? I'm looking for subgroups of order 3, right? So in order for us to have a subgroup of order 3, we either need to have, well, it forces us to have the order of A to be 1 and the order of B to be 3. We can't have the order of A to be 3 because that doesn't divide 4. So we're out of luck there. I mean, we're in luck there. That's not a possibility. Thank you. Because I like not having a possibility. All right, there's just one case. Wait a minute. Oh, I'm sorry, I'm in this specific context.
There's multiple contexts.
Yeah. Why am I saying no good? Oh, I think I was just counting in my head, like there's not enough here because, oh, there's not enough here. I mean, that's just 2. There's 2 elements of order 3. It's not enough. We're looking for something with 13 elements of order 3. So if I look at this one, 4, 3, 9, so I've got ABC, I need at least common multiple of 3. That means I need either 1 here, 3 or 1 here, 3 or 1 there, right? So there are 2 plus 1 ways to do that, 2 plus 1 ways to do that. So there are 9 elements of order 3 in here. So that's not going to do it either, right? But in this one, Z4, Z3, 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 you watch. I have ignored this error up here in my analysis down here. I didn't even see it, like I'm an idiot. Let's see here. So in here, you've got ABCD, and you can have order 1 or 3, order 1 or 3, order 1 or 3. So you got 3 times 3 times, I said break it into cases. I have to be careful with my counting here. So if the order of B is 1, if the order of B is 1, then the order of C is 1, and the order of C is 1, that forces me to have D equal to 3. There are 2 choices there. A1, order of C being 3, D1. Well, there are 2 choices for this, and this just 1 choice for that and that. But what do I say here? Oh, 1 or 3. Sorry, I lost track of my. If this is 3 and that's 1 or 3, that gives me 2 for here and 3 for here, so there's 6 total. And then we're in the next case. If this is 3 and this is 1 or 3 and that's 1 or 3, I mean, right, then there's 2 choices for here. Excuse me, there's 3 choices for here. There's 3 choices for here because you've got 2 elements of order 3 or 1 element, 1 identity. So 3, 3, and then that's, of course, 2 choices here. So I've got 2 times 3 times 3, 18 choices. So 26 elements of order 3 in here. And for nearly the same reason, yep, there. And of course, if you have 26 elements of order 3, every subgroup of order 3 comes with 2 generators. So you divide by 2, that gives you 13 subgroups of order 3. So, sorry if my counting is clear as mud, but I don't know. I sometimes think less writing in terms of counting maybe is more. I don't know. I don't have a universal rule for how to count these things. You know, I just kind of do it as it comes to me. So. Yeah. Yeah. I think. Well, anyway. Let's see. 16. So 17. Down to 17 here. Unless, of course, you guys had a question about something specifically. But you had a question about this one in the email, Lane, I remember. This problem.
Yes, I did.
So this is the commutator subgroup, X inverse, Y inverse, X, Y is in G. That is the so-called commutator subgroup, all right? So, and this is generator notation. So like this means that this G prime is created by taking products of these sorts of things, all right? And so we're supposed to prove that, just to be clear, a typical element of this G prime is like A to the I1, A to the I2, AK to the IK, where the I's are plus or minus 1. In other words, it's the element or the inverse of the element and the A sub i's are formed from these, which happen to be these guys. All right, that's what a typical element in the commutator subgroup looks like, just elaborating on that. We're supposed to prove that G prime is a characteristic subgroup. Now that's defined in number 1. Number 1 told us that N, a subgroup of G, is a characteristic subgroup if it is a fixed subgroup of the automorphism group. In other words, if everything in the automorphism, every automorphism of G fixes N, then it's a characteristic subgroup. So here it is. Let phi be an automorphism. Let x and y be in G. Notice that phi of x inverse y inverse xy is equal to that by the homomorphism property. But we also can pull inverses out of homomorphisms, even though, I mean, phi is an isomorphism, but, you know, this we also know for homomorphisms. But this is just a particular group element, right? Something inverse times A times B, just to emphasize, it's again, you know, this is a generator. This is a generator in the commutator group, and this is another generator in the commutator group. So it's sent a generator in the commutator group to a sent generator in the commutator group, and you can generalize, right, that if I take a general element in the commutator group, well, by properties of homomorphism, this is equal to that. But we've already proved that this is an element of the commutator subgroup by this calculation up here. So this is a product of things in the commutator subgroup. So it's again, an element of the commutator subgroup. I am assuming that we know that the commutator subgroup is a subgroup. I don't think we were asked to prove that it was a subgroup. If we were, there's a gap in my solution. I don't think we were. So the point then is this is something in the commutator subgroup, something in commutator subgroup, something in the commutator subgroup, either it or its inverse, but you know the inverse of something in the commutator subgroup is in the commutator subgroup. So consequently, we've shown that the image of something in the commutator subgroup is again in the commutator subgroup, provided that we're working with an automorphism of G. Consequently, G prime is a subset of phi of, phi of G prime is a subset of G prime. But you can use exactly the same argument for the inverse of the isomorphism to say that phi inverse of G prime is a subset of G prime. So you've got this and that, which means that they're equal. In other words, G prime is a characteristic subgroup. I mean, to show that it's a subgroup, you got to show it's you know, I don't think there's much work to do there really. Clearly the identity's in there, so it's not empty. And if you take the product, of two things like this, right, then you just got a longer string of the same kind of object. So it's still in there. And the inverse is in there because if you use sock shoes here, the inverse of this is just a KIK inverse, which is a KI minus IK on down the line. So again, but minus IK is just the same as one. I mean, minus plus or minus 1 is still minus plus 1. So it's easy to see that the inverse of this is again in the commutator subgroup. It's not hard to prove the commutator subgroup is a subgroup. Extended sock shoes.
Like,
K-fold sock shoes.
Extended, it works the same for like other elements. It just flips the order of them. Small inverse.
You can prove that by induction. I could put it on the test.
I knew he was going to say that.
Yeah. Okay.
There's a lot you can put on the test.
Fair enough. There is a lot. Okay, so we're supposed to prove that if H and K are subgroups, then we define the product of H and K by that. This may or may not be a subgroup generally, all right? But this condition, here's KH, right? HK is a group if and only if HK is equal to KH. So I'll prove the converse direction. Suppose HK is equal to KH. You take A, B, and this. What I'm aiming for is one-step subgroup test. Why do people always talk in the hallway? I just... Is there a class in here or something? Or?
Waiting for the door to open.
Oh, okay, okay.
Are we too loud?
Yeah. Are we too loud? All right, so so A and B in HK, that means that A is equal to H1K1, and it's also equal to K1H1 because it's in both. We're assuming these are equal, right? So everything in here is also in here. So I can either write it as H times K or as K times H for appropriate choices of the...
Supposed to be K1, H1 there?
Here? No, not at all. They don't have to be the same elements. The sets are the same, but the representation of a particular element we shouldn't assume is the same points. No. No, not at all. So there exist some points, some elements in K and some element in H such that K2H2 is equal to A. Likewise for B, you can either write it as H3K3 or for some possibly different choice, K4H4. Now, of course, if we're in an abelian group, the same H and the same K will work, but we shouldn't assume that from the outset. Now, AB inverse is exactly this, and so then you use sock shoes, and so sock shoes gives me this, but then what you do is I look at this, K1, K3 inverse, that's in K, this is in H, so this is in KH, which means it's also in HK, so there is some H5 and K6 that I can rewrite this as, because these sets are equal. And then now, voila, I've got something in H, something in K, so I proved that AB inverse is an element of HK, which shows it's closed. And then to show it's not empty, it's easy to see that E is in both, so EE is in HK, which is not empty, one-step subgroup test, subgroup. Now, the other direction, because it's if and only if, right, is we want to show that HK is a subgroup of G. Suppose HK is a subgroup of G. If X is in H, of course we have X is in HK, which means that H is a subset of HK. Also, as H is a subgroup, that means that H is in fact a subgroup of HK. Because it's a subset which also has group structure, and it's all the same group structure here, so, all right, subgroup. Likewise, K is a subgroup of HK by almost the same argument, right? So if you take Z and KH, what do I want to do? I want to show that KH is a subset of HK, is my goal. So Z is that, it's K times H for some H. Okay, so Z is formed by products of elements in there, right? So what's that mean? See, my argument here is if Z is in KH, it's equal to a product of something in a subgroup of HK and something in a subgroup of HK. So it's still in HK. So thus Z is an element of HK, which shows you that KH is a subset of HK. KH is a subset of HK. Conversely, if you take a point in here, right, that means we can write U as H1 as H2 K2, and since that's a subgroup of G, that means there's some A, which is the inverse, whose inverse is this, right? Every element is the inverse of some other element in a group, and so then let's see here, getting to the point. That means A. All right. So A is equal to H3 K3. All right. Yeah. Closed are under A.
Yeah.
A is always A inverse inverse. Yeah. Anyway, so you work through this, and that gives you that the U I picked in here is also in KH, which shows that HK is a subset of KH, and so we get that they're equal. Nothing particularly tricky. I think the trickiest thing in here maybe is this idea that if I have, this is a subgroup, and I have this as k times h, realizing that that is that's an element of hk, and this is an element of hk. So the product has to also be an element of hk because hk is a subgroup. That's where we're using that it's a subgroup, really, right there. So problem 67. Yeah, this one I liked. See here, U144 is U3, it's 9 times 36, right? Wait a minute. Sorry, 9 times 16. Yeah, I'll get with it eventually. So this, by our theorem, is z to the 3 squared minus 3 to the 1. So that's z6. 2 is funny, right? This is 2 to the 4th. That's... Uh-oh. Hello? Not yet, but pretty soon. Yes? What would you... Okay. Okay, I will call you when I'm at Walmart to get the particulars, okay? Okay, bye-bye. I need to buy paint. Hannah's making a butterfly of some sort. Fabric paint. Anyway, so this messed me up to start with because I was like, oh, so it's Z16 minus Z minus 8. No. It's a different rule for 2. 2 is not like the others. So 2 to the 4th is, where do I have it down here? U to 2n is Z to the 2n cross Z to the 2n minus 2. So that's the 4 minus, have I done this wrong? See, that would seem to suggest to me Z to the 16 cross. Maybe I've copied this down wrong. Something here is askew. I don't know. If you look in Galilean,
17.
I would look in around page 160 of Galilean. Try to find where he...
I remember seeing that in lecture notes.
The Z is
I mean, we're supposed to show that these are isomorphic, right? So... Oh, it's 2n minus 2. That would be... That'd be the Z4. Maybe this is just supposed to be Z2 without the n. Yeah. This is a typo. That's not supposed to be n. Right there, that n is the offending thing. Is that a dot or an n? I don't know if this is a dot or an n. But that should just be, I think it's just Z to the 2n minus 2 cross Z2. For example, let's try 8. N equals to 3, right? N equals to 3. Oh, that won't help. Dang it.
Right here it is U to the n power. It's like isomorphic to Z2.
U.
U2n.
Mm-hmm.
Isomorphic to Z2 cross Z2 to the n minus 2 power.
Yeah.
And n must be greater than 3.
There we go. This is the correct result. Now, that's here. Basically, we can look at it this way. There's a typo in my solution at the moment. This should just be, scratch out that 2. It should be just Z2 cross that. And this should be, or which is isomorphic to Z2 to the n minus 2 cross Z2. And that's not an n, that's a period. This is right. Okay. which is good because that's what we get down here, right? This is easier because this is just 4 times 5 times 7. Those are relatively prime, so we get the direct product of the unit groups, and that is isomorphic to Z2, which is easy to figure out just by counting. Numbers relatively prime to 4, 1 and 3. There's 2 of them, it's Z2, okay? We don't need some fancy schmancy. I mean, even for U8, we don't need a formula. We already know U8 is Z2 across Z2. We saw that in the last test, 1, 5, 7, 3. Yeah, that's right, that's right. And this is prime, so that's Z4. That's prime, that's Z6, all right? And as you can see, they're isomorphic because you can switch around the order of things, right? Me too. I was just like, la la la, oh, I got this. And then I'm like, wait a minute, oh, odd prime. Doofus. All right, so I'm going to try to finish explaining this homework, and then we'll pick up. Well, I don't know, I might cheat and do another 5 minutes here. So suppose H and K, G, H, K are finite groups. You have the internal direct sum of, direct product rather, of, and people would dispute my notation, some of people, but whatever. I do mean internal direct product here of G and H, and internal direct product of G and K. In other words, the intersection is the identity. They're normal subgroups of some supergroup G prime, and they're equal. All right, but anyway, I don't know if I need all that. I'm just reminding what I mean by that notation. Okay, so we also have proved that there's a unique G and H that represent each Z in the direct product of G and H. Z is equal to GH for some unique G and unique H, right? Likewise, Y is equal to GK for each Y in here. I mean, there's a specific G and K for each Y. I don't mean to say that this G and that G are in any way related necessarily, except to say that they're both from G. Big G. All right, so here's the argument I'm going to use. Phi goes from here to here. I'm going to define it by phi of GH equals to H. Now, this has the image just being H. You can easily see that any H is obtained. So it's on to H, and it's all that it's on to, right? You can't get G from here. So it's pretty easy to see that the image is H. The kernel, well, if you set this equal to, the identity, that forces this to just be in G, so the kernel of phi is in G. The kernel of phi is equal to G. It's also clear that this is an isomorphism. A homomorphism, you can work it out. And so G, H mod the kernel, G, is isomorphic to H. But by almost the same construction, we can show that the direct sum of G and K by G is isomorphic to K, right? Just use the mapping phi of GK equals to K, going from G plus K to G plus K, so to speak. All right, but these two sets are equal, so the quotient by G are equal, and that then implies, since these two things are equal, that these should be isomorphic. Oh, man. So this equality comes because I'm assuming that this internal direct product is equal to that internal direct product. So if I quotient by G, it's the same quotient space. G is a normal subgroup. We've proved that it's the kernel of a homomorphism, so it's normal. We can take this quotient. And also, we're assuming it's normal up here, so duh. Okay. So that's isomorphic to H, but that's isomorphic to K. So H is isomorphic to K. And by the way, there's nothing finite here. So part B is bogus. Yeah, there is no counterexample. Yeah. Now, if instead of equality here, you have isomorphism, in the initial statement, well, then it's a different story. But the equality is a big condition. Now, this I think is what was in my brain, something like this. If you don't take internal products, if you just have products, like the product of G and H is equal to the product of G and K. Suppose that these are both groups. Does it imply that H is isomorphic to K even when G is equal? No. For example, non-zero reals times non-zero reals is in fact equal to non-zero reals times the identity subgroup, right? These are definitely equal as products because they're both equal to Rx, and yet this is not isomorphic to that. So if you drop the independence of the spaces that you're taking the product of, it's much easier to find counterexamples to canceling. That's not especially surprising. Here's C. In the infinite case, my go-to would be just vector spaces, right? In vector spaces, you can write R2 as the direct sum of the x and y axes, because these are two axes. You take points on the x and y axis, you add them together. Any point in the plane you can obtain, so it's the sum of x and y axes is the plane. The intersection is just the origin, so it's a direct sum. And likewise, you can take any point in the xy plane and obtain it from adding, vectors along the x-axis to a vector along the line, y equals x. In short, this subspace and that subspace form R2 by the direct sum. And of course, this and that are equal, but this is not equal to that. So in order to be able to cancel direct sums, you need something extra, like orthogonality of the sums. Even so, well, anyway, cancellation is a dangerous game. Okay, let's just say that. Definitely. And then here, in the finite case, you can have, if you look at the Klein 4 group, it gives you the examples you're looking for. So if I take direct sum of G and H, or if I take the direct sum of H and K, I'll get the Klein 4 group. And then let me just be more explicit down here. So it's easy to see that these intersect at the origin, just the zero. So the intersection is just the trivial group. And the sum of G and H is Z2 cross Z2. The sum of G and K is also Z2 cross Z2. Do you know what I mean here? You take all possible sums. So obviously you get G back and you get H back, right? How do you get the other point you're missing, this one? You just add this and that, right? This plus that gives me 1, 1. And then when you look at G plus K, how does that give me? Well, obviously all of G is in there and all of K is in there, right? How do you get the other thing you're missing, the 1, 0? Well, you just add this and that. That gives me 1, 0. So this plus that gives me 1, 0. So as you can see, GK has everything in G, everything in K, and everything that's not there. It's the whole Klein 4 group. So these are equal, and yet obviously H is not equal to K. Is H isomorphic to K? Certainly. They're both isomorphic to Z2. Any questions? So I think that gets us to 18. Was that the last one I have posted so far? Oh, man. Yeah. Yeah, this one. Yeah. That one was hard. Let's see here. But anyway, I'll talk about those Thursday because we're out of time. And as you have heard, I need to go get paint. So, thanks, guys.
Thank you.
Yeah, that problem one should be called Geometry's Revenge, because it is utterly trivial to see what the answers are. Oh, thank you. In terms of just geometry, like what's the orbit of a rotation? What's the orbit of a point under a rotation? It's a circle. What's the orbit of the origin under a rotation? It's the origin. What are the stabilizers? Well, nothing stabilizes a point except for the identity, and if you think about it for a while, the reflection that stabilizes the line that's on that point.
Yeah.
But to actually show that by algebra required a significant effort on my part, more than I was expecting.